In this presentation, I'll be explaining analysis of three-phase full converter. Now this is the full converter topology in which there are 6 silicon control rectifier switches, and here the upper switches T1, T3, T5, somewhere like that one, and the lower switches are marked as T2, T4, T6. Why this is marked in this order means the switching sequence will be in the order T1, T2, T3, T4, T5, T6, again T1. Now to make the switching sequence in that, we have numbered like the T1, T3, T5. These are called the positive group of SCRs, and these are called the negative group of SCRs. And this is the RLE load, what we are considering it. And we are assuming that's a continuous conduction in which the load current is assumed to be constant. Capital I node is the load current. And the voltage available across the load is the average DC voltage will be available. Input is a 3-phase AC voltage. And here, this is the phase voltage of phase A, phase B, and phase C. They are 120 degree apart. And the corresponding line voltages are drawn below that one. Line voltage means VAB equal to VAN minus VPN actually. And similarly, we are calculating what is VBC, VPN minus VCN. Like that, all these voltages are calculated and that is drawn here. The lower one is the line voltage. This is the phase voltage. And here, this is, I told you, the positive group of SCRs, and this is the negative group of SCR. And at any instant, one from the positive group and one from the negative group will be conducting. And depending upon that one, you will be getting the corresponding line voltage across the RLE load. For example, if just come to here initially here T1 and T6 are conducting here. If you see that one, T1 and T6 means from positive group T1 is conducting and from the negative group T6 is conducting. Therefore, the voltage is T1 here. T5 and T6 are conducting here. T5 and T6 are conducting. T5 from the positive group and T6 from the negative group. Since it is T5 is conducting here, C phase is connected to here when this is conducting. And T6 means that this is conducting, phase B is connected. Therefore, this voltage will become, it is equal to VCB. The voltage will become VCB. That is, here the line voltage will be available here. Now, one more thing is that what we are concerned here is the firing angle equal to 30 degree. Always the firing angle is calculated from for example, in this the meeting point of these phases voltages. This is from this one the firing angle for phase A is calculated, and from this one the firing angle for phase B is calculated, and from this the firing angle for the phase C is calculated. Therefore, in this case, alpha is made 30 degree. That from here 30 degree is taken. At this instant, T1 is fired. And before T1 is fired, from the positive group, T5 was conducting, and from the negative group, T6 was conducting. That's why I told you, T1, T5 and T6. And then the voltage was here, TCB was the voltage across the RLE load. And when T1 is fired here, at alpha equal to 30 degree, when T1 is fired from, that is, when T1 is fired, the incoming SCR equal to T1 and the outgoing SCR is equal to T5. From the positive group, the transition happens from the T5 to T6. Still, the negative group T6, T1, from T5 to T1, and still the negative group T6 is conducting. Therefore, here T1 means the phase A comes here, and T6 means here phase B is coming. This voltage, the voltage across the RLE load will be the line voltage VAC. Therefore, that is why here the voltage is equal to the voltage, this is equal to B phase, and this is the phase voltage equal to A. Therefore, this voltage will become VAB. That is, this voltage is equal to VAB. Similarly, after, again, 60 degree, T1 is fired. Then again 60 degree, T3 is fired. Then again 60 degree, T4 is fired. Again 60 degree, T5 is fired. Again 60 degree, T6 is fired. Then again T1. So the firing sequence is T1, T2, T3, T4, T5, T6. Each switch is triggered up 60 degree interval here, and we can see that each switching device is conducting for 120 degree duration. Therefore, here based on the SCR conducting from the positive group and the SCR conducting from the negative group, you will be getting corresponding line voltage will be available across the load. What is the maximum positive voltage in this phases, that the corresponding thyristor will be conducting from the positive group. Similarly, in the negative group, which line has got a maximum negative voltage, from that one it can conduct. Only means you have to give the firing signal. It is ready, it is forward bias. For maximum voltage on the line voltage is positive, that from the positive group, that SCR is forward bias, and that can be triggered, then that will be conducting. Similarly, maximum negative voltage on the negative group of SCRs like T2, T4, T6, then that is ready to conduct. Then if you are giving the triggering signal, that will be conducting. Based on the SCR conducting on the positive group and based on the SCR on conducting on the negative group, will be the corresponding line voltage will be available across the RLE load. And the average voltage across that one is, you can calculate, we already derived in the previous presentation, like average voltage equal to 3√3 Vm by pi into cos alpha. This is the average voltage across the load. Now here the different thyristors that are conducting is marked here. This is a positive group of thyristors, that is this one, and this is a negative group of thyristors. At any instant, one from the positive group and one from the negative group will be conducting, and you will be getting corresponding line voltage across the RLE, this is a load. And what we are assuming is that the load current is continuous, like say constant current is flowing through the RLE load. And here, if you watch the current through the input source here, for example, IA current. If the current, the thyristor, say T1, for example, if current thyristor T1 and T2 are conducting, the current flow is from this line through T1 and returning back through the RLE load again to T2, and then it's returning back to the C. Then the current through this one is positive direction, that there will be a current, and the magnitude of that current is same as capital I naught, and the current is flowing through this one, through the line IA. And when none of these thyristors are conducting, that is T1 and T2, T4 are not conducting, here the current through the line IA equal to 0. And when T4 is conducting, other than T1, if T4 is conducting, in that case the current flow will become opposite. That for example, if you are considering the current here, during this duration, you can see that when T4 is conducting, once the current flowing through the T4 here, T4 conducts, the current flow will be opposite direction. The source current will be opposite direction. The same magnitude of current, but it will be minus I naught. That is why you are getting a minus I naught. Therefore, here from alpha, and that is from, you'll be measuring the firing angle from 30 from this point, and from that one alpha is attaining alpha is 30 here, and this point is 30 plus alpha here, because the shift is 30, is the 30 plus alpha to 150 plus alpha. You can see that one T1 is conducting. Once T1 is conducting, the current is equal to plus I naught, plus whatever this load current. And when from this 150 plus alpha, this is equal to 210 plus alpha, 210 plus alpha. During that period, either T1 or T4 are not conducting, or T1, T2 are not conducting. None of these thyristors are conducting. That is why this current IA equal to 0. That is from 210 plus alpha, 150 plus alpha to 210 plus alpha, that's no current. From 210 plus alpha to 330 plus alpha, that is the thyristor T4 is conducting in the leg A. That is, we can see that one, looking from this one, T4 is conducting. Once the thyristor T4 conducts here, the current direction through the source side is opposite to that one. Again, the magnitude is equal to I naught, but the current direction is opposite, that is why it is equal to minus I naught. Again, from this 330, it is again 0. Therefore, this is the source current through the line A. IA, it is marked as IA. So actually, it's the source current through the line A. Like that, you can draw what is the source current in the phase B and phase C. All are 120 degree apart. Therefore, this is the constant load current, and this is the source current in the phase A, and this is the devices or the switches that are conducting different durations, and for firing angle alpha it is drawn. This is the voltage across the RLE load, and the firing sequence is equal to T1, T2, T3, T4, T5, T6, and all are fired 60 degree interval. So this is the average voltage. Now let us see the analysis of three-phase full converter or six-phase converter. This is the, as we have seen, this is the source current in the phase A. From alpha plus 30 to alpha plus 150, it is plus I naught. That is, I naught is the continuous load current. And from alpha plus 150 to alpha plus 210, it is equal to 0. From alpha plus 210 to alpha plus 330, it is equal to minus I naught. Like that one, again it is equal to 0. Therefore, this is the source current in the phase A, and we are going to analyze the source current, and you are going to find out what is the distortion factor, what is the displacement factor, what is the power factor, what is the total harmonic distribution, etc. For doing that one, we have to do the Fourier analysis of this waveform. This Fourier analysis, general equation for Fourier series is that the function or this current ist is equal to a DC component of the current, that is A naught, plus sigma n equal to 1 to infinity an cos n omega t plus bn sin omega t, where the Fourier constant a naught, this is an, and bn are the Fourier constants as such. And but here it is having a property like half-wave symmetry is there. Half-wave symmetry means that ft equal to minus of ft plus t by 2. For this waveform, ft equal to f minus of ft plus t by 2. Because of that one, there's a half-wave symmetry. If this waveform is having a half-wave symmetry, then Fourier constants like a naught will become equal to 0 and n equal to 4 by t integral 0 to t by 2 ft cos n omega t. It's a generalized equation. But in this case, the limits are alpha plus 30, that is 4 by t equal to 2 pi integral alpha plus 30 to alpha plus 150 I naught. I naught is a constant current here. I naught cos n omega t. Cos n omega t d omega t. This is for n odd. Even it is absent. Only for odd it is present. That is A1 is present, A3 is present, A5 is present, A7 like that. Only odd is present. Similarly, Bn equal to, general equation is 4 by t integral 0 to t by 2 ft sin n omega t d omega t. But in this case, substituting for this limit like alpha plus 30 or 4 by time period equal to 2 pi. 4 by 2 pi integral alpha plus 30 to alpha plus 150. Doing this for this one. That I naught, that is I naught into sin omega t d omega t. Again, it is equal to, for odd it is present. That is B1 will be there, B3 will be the sin n omega t d omega t. B1 is there, B3 is there, B5 is like that. Even, Fourier constants of B are absent. Therefore, you know the equation, what is Bn as well as An. Now, if you substitute n for different values, for example, n equal to 1, you'll be getting what is A1. Therefore, A1 equal to 4 by 2 pi integral alpha plus 30 to alpha plus 150 I naught cos omega t d omega t. Now, we'll be deriving the equation in the next slide. The equation is equal to, it is equal to minus 2 root 3 divided by pi into I naught sin alpha. Similarly, in this equation, Bn equation, if you substitute n equal to 1, B1 equal to 4 by 2 pi integral alpha plus 30 to alpha plus 150 I naught sin omega t d omega t. It will be getting 2 root 3 divided by pi into I naught cos alpha. Therefore, this is the equation for B1 Fourier constant, and this is again the Fourier constant A1. That corresponds to fundamental. A1 and B1 are the Fourier constants corresponding to the fundamental. Now let us derive the Fourier constant corresponding to fundamental A1 and B1. We have given the result in the previous slide. The derivation is given here. A1 equal to 4 by 2 pi integral alpha plus 30 to alpha plus 150 I naught cos omega t d omega t, or 4 I naught divided by 2 pi integration cos omega, that is sin omega t alpha plus 30 to alpha plus 150. 4 I naught divided by 2 pi the sin alpha plus 150 minus sin alpha plus 30, or 4 I naught by 2 pi sin alpha plus 150 can be written as alpha plus 90 plus 60 minus sin alpha plus 90 minus 60. For sin A plus B minus sin A minus B, where A equal to alpha plus 90 and B equal to 60. Sin A plus B minus sin A minus B equal to 2 cos A sin B. Therefore, 4 I naught divided by 2 pi into 2 cos alpha plus 90 into sin 60. Or substituting that one, will be getting 2 into cos alpha plus 90. It is equal to minus sin alpha into sin 60. We'll be getting minus 4 I naught divided by 2 pi, 2 sin alpha into root 3 by 2, or minus 2 root 3 I naught divided by pi into sin alpha. This is the Fourier constant A1. And for corresponding B1 equal to same 4 by 2 pi integral alpha plus 30 to alpha plus 150 I naught sin omega t d omega t, or 4 I naught divided by 2 pi integral sin omega t minus cos omega t. Limits are alpha plus 30 and alpha plus 150. Now make it as cos omega t. The limits will be reversed as such. Now it is equal to 4 I naught divided by 2 pi into cos alpha plus 30 minus cos alpha plus 150. Again, this alpha plus 30 can be written as alpha plus 90 minus 60, and alpha plus 150 can be written as alpha plus 90 plus 60, or cos A minus B minus cos A plus B, where A equal to alpha plus 90 and B equal to 60. Therefore, 4 I naught by 2 pi into twice sin A cos B. Therefore, 2 sin alpha plus 90 sin 60. Again, we'll substitute here 4 I naught divided by 2 pi into 2 cos alpha into sin 60. 4 I naught divided by 2 pi into 2 cos alpha into sin root 3 by 2, or that is equal to 2 root 3 I naught by pi into cos alpha. Therefore, the value, the Fourier constant for fundamental B1 equal to 2 root 3 I naught by pi cos alpha, and the constant A1 equal to minus 2 root 3 I naught by pi sin alpha. Therefore, in the previous slide, we calculated or we derived equation for the fundamental Fourier constant A1 and B1. A1 equal to minus 2 root 3 I naught by pi sin alpha. B1 equal to 2 root 3 I naught by pi cos alpha. Once you get A1 and B1, we can calculate what is the maximum value of the fundamental. Maximum value of the fundamental. These are Fourier constants corresponding to fundamental A1 and B1. From these two values, you can calculate what is the maximum value of the fundamental signal, which is equal to root of A1 square plus B1 square. Once you get the maximum value of this fundamental, root of A1 square plus B1 square, then you can calculate what is the RMS value. RMS value is equal to maximum value divided by root 2. Therefore, root of A1 square plus B1 square divided by root 2, which is equal to substituting these values of A1 and B1 here, root 6 I naught divided by pi equal to 0.78 I naught. For example, if the load current equal to 10 amperes, it will become 0.78 into 10 or 7.8. That is the RMS value of the source current, provided the source current equal to 10 amperes. This is next one. We have to find out what is the RMS value of the total signal. What is the RMS value of the total signal here? To find out the RMS value of the total signal here, IS, that is a IS actually. This is IS1 and this is IS. IS equal to square root of 1 by pi integral alpha plus 30 to alpha plus 150 I naught is a magnitude I naught square d omega t, or it is, yes, root mean square. These are squaring, and then you are calculating what is the mean and then take the square root. Therefore, it is equal to root of 1 by pi I naught square omega t. The limits are alpha plus 30 and alpha plus 150. And substituting that one, we are here square root of 1 by pi I naught square alpha plus 150 minus alpha plus 30, or alpha cancels, and here we'll be getting it is equal to I naught square divided by pi. Then we'll be getting 150 minus 30 will come 120. Corresponding in radians, it equal to 2 pi by 3. You are substituting that in 2 pi by 3, which is equal to root of 2 by 3 into I naught, or 0.8165 I naught. Therefore, the RMS value of the total signal, this is actually the source current in the phase A. This is the source current in phase A, alpha plus 30 to 1 alpha plus 150 plus I naught, and from here to here minus I naught. During this period, equals 0. Now, if you calculate the RMS value of the total RMS value of this source current, which is equal to 0.8165 I naught, and the RMS value of the fundamental equal to 0.78 I naught. For example, if again 10 ampere is the load current, constant load current that is flowing to RLE load, it will become 8.165 amperes. Therefore, that is the source current of the total signal, and this is the source, the RMS value of the source current, and this is the RMS value of the fundamental. Now, one more parameter we have to find out, what is the phase shift. Phase shift means It is the phase angle between the fundamental voltage and fundamental current. That can be calculated by the equation phi1 equal to tan inverse A1 by B1. A1 is this one and B1 is this one. If you take the ratio, you will be getting it is equal to minus of sin alpha divided by cos alpha minus tan alpha. Therefore, tan inverse minus tan alpha, which is equal to minus alpha. Therefore, the phi1 equal to minus alpha, and we have calculated what is the RMS value of the fundamental 0.78 I0, and the total RMS value equal to 0.8165 I0. Therefore, this is the circuit topology, but already we have discussed. And through this is a constant current is flowing through the RLE load. It's a continuous conduction in which the current is continuous. It's a constant flowing to I0 is flowing through that one, and the current through this phase that is drawn here, and we have calculated what are the source current RMS values for total for the fundamental as well as the total IS and IS1, and the phase shift corresponding for the fundamental, which is equal to phi1 equal to minus alpha. Next, we'll be calculating what is the displacement power factor. Displacement power factor is the cosine of the angle between fundamental voltage and fundamental current of cos phi1. Cos phi1 is already minus alpha. Therefore, cos phi1 equal to cos minus alpha, which is not the same as cos alpha. That is the displacement power factor. And distortion factor is the ratio of the RMS value of the fundamental to the total RMS value. We take the ratio 0.78 I0 divided by 0.8165 I0, then we'll be getting 0.955. For this form, distortion factor equal to 0.955, and this is the displacement power factor. And the total input power factor is given by that the input power factor of the line, which is equal to the fundamental RMS, the active power. This is the fundamental active power divided by the apparent power. Therefore, Vs into IS1 into cos phi1. This is the fundamental active power divided by apparent power. Vs into Is. Vs cancels, or IS1 divided by Is into cos phi1. IS1 by Is is already we are defined as the distortion factor, and cos phi1 is equal to displacement power factor. Therefore, the total power factor is the product of displacement power factor and the distortion factor. So this is the distortion factor and this is the displacement power factor, and the product is equal to the total power factor, which is equal to 0.955 into cos alpha. Now, the total harmonic distortion, it is the ratio of the RMS value of the harmonics to the RMS value of the fundamental. Therefore, square root of IS square minus IS1 square. This is the RMS value of the harmonic component, or we are, that is with respect to fundamental signal RMS value IS1 we are calculating. The square root of, substituting here, 0.8165 I0 whole square minus 0.78 I0 whole square divided by 0.78 I0, which is equal to 0.3095, or it can say that in percentage it is 30.95%. So the total harmonic distortion for this waveform is 30.95%, and distortion factor equal to 0.955, and displacement power factor equal to cos alpha. For example, if alpha equal to 30, we can have to substitute 0.955 into cos 30 is the total input power factor. Now let us see an example. In a three-phase full converter with RLE load for a firing angle of 30 degree and a constant load current of 10 amperes, phase voltage is 230 volt. Calculate the average output voltage, displacement power factor, distortion factor, power factor, and total harmonic distortion. The circuit topology is this one. This is the input three-phase signal is given, VA, VB, VC, phase voltages T1, T3, T5, T2, T4, T6, and the RLE load. And through this one, a constant current I0 is flowing, and that I0 is given as 10 amperes. 10 amperes the constant current that is flowing through RLE load. And here, the firing angle equal to 30 degree. Firing angle of this each thyristor is given as 30 degree. Now, if you draw the corresponding current through the phase IA, for example, phase A here, it is like this one, already we have seen. And here, from alpha plus 30 to alpha plus 150. And here alpha you can substitute 30, or 30 plus 30 plus 30 plus 150. During this period, the corresponding current is equal to plus 10 amperes. And from alpha plus 150 to alpha plus 210, it is equal to 0. And from alpha plus 210 plus alpha plus 330, it is equal to minus 10 amperes. Therefore, this is the shape of the current through the phase A. You are asked to find out what is the distortion factor of this one, what is the displacement power factor, what is the total harmonic distortion, what is the input power factor, etc. Now, first, the question is that what is the average output voltage? Is, as you know, that one already we have derived equation for the average output voltage, which is equal to, average voltage is equal to 3 root 3 Vm by pi into cos alpha. 3 root 3 Vm by pi cos alpha, or 3 VML by pi cos alpha. Therefore, Vm is the maximum phase voltage. Here, Vm is the maximum phase voltage. 3 root 3 maximum phase voltage. RMS value is given as 230 volt. Therefore, the maximum value equal to root 2 times 230. Therefore, 3 into root 3 into root 2 into 230 divided by pi into cos firing angle equal to 30. Cos 30, which is be getting 465.9 volt. Therefore, the average voltage available across the RLE load is given by 465.9 volts. First one. Next is average output voltage calculated. Constant load. Load current is constant. 10 ampere is flowing through this one. And the firing angle is given as 30 degree. The displacement power factor. Displacement power factor is the cos phi 1. Cos phi 1 means where phi 1 is the phase angle between the fundamental voltage and fundamental current. That is as given as alpha. Phi 1 equal to actually minus alpha, but cos minus alpha is same as cos alpha. Therefore, cos 30 0.866. Cos 30 equal to 0.86. This is the displacement power factor. And distortion factor is the ratio of the RMS value of the fundamental to total RMS value. IS1 divided by IS, or 0.78 I0 divided by 0.8165 I0. That's already we have derived in the previous slide. It is been derived. For 0.78 I0 divided by 0.8165 I0, I0 gets cancelled. The particular 0.955. Therefore, 0.955 is the distortion factor and displacement power factor equal to 0.866. Therefore, the total input power factor is the product of displacement power factor and distortion factor. Actually, it is the ratio of the fundamental active power to the apparent power. It is nothing but it is a product of displacement power factor and distortion factor, which is equal to 0.86 into 0.955. It is equal to 0.827. So the input power factor here is equal to 0.827. And the total harmonic distortion is the ratio of the RMS value of the harmonic current to the RMS value of the fundamental. Therefore, root of IS square minus IS1 square. Therefore, divided by IS1. It is square root of 0.8165 I0 all square minus 0.78 I0 square divided by 0.78 I0. Then we'll be getting it is equal to 0.3095 or 30.95%. Therefore, that is the total harmonic distortion.